Okay, this is topic 7, question 1, part 1. Okay, first of all, define the term unified atomic mass unit. Okay, the unified atomic mass unit, 1 AMU, equals 1/12 the mass of one atom of carbon-12. All right, that's it. Okay. Now B, the mass of the nucleus of Rutherfordium-254 is 254.1001 atomic mass units. Calculate the mass in electron volts. Okay, so what I need to do is I have to take this mass here and convert it into the mass in giga-electron volts per c squared. Okay, and if it was just asking for the energy, it would just be giga-electron volts, but it's asking for it in GeV times c divided by -2, and that has to do with the E equals mc squared equation. All right, so we got 254.1001 AMU. And we're going to multiply this. If you look in your formula packets, you'll find it by 931.5 mega electron volts. So we're going to have to convert it to giga electron volts because we have mega electron volts here. Okay. -2. When I calculate this out, you might want to stop it and do the calculation on your own. You get 236.601 mega electron volts. Okay. Okay. And now I have to convert this into giga electron volts. There's 1,000 mega electron volts and 1 giga electron volt, so I just divide it by 1,000. Divide it by 1,000 equals, that's mega electron volts per giga electron volts. And I end up with 236.7 mega electron volts. Okay, that is it. Next part of the problem. Okay, in 1919, Rutherford produced the first artificial nuclear transmutation by bombarding nitrogen with alpha particles. The reaction is represented by the following equation. I have to identify X. Okay, I know that this is a hydrogen nucleus because I've taken an alpha particle and I've added 3 total nuclides because the total number of nucleons in the nucleus is now 17, and there's 1 proton. So I've added 2 neutrons, 1 proton. So what I end up with is just 1 proton. Okay, so hydrogen nucleus or proton would be the answer. All right, next question. Okay, this is a little bit longer. The following data are available for the reaction that was given in the last question. All right. So in that question, I had an alpha particle plus nitrogen 14 yields oxygen 17 plus X. Okay. I'm just going to write it right here. That's an alpha. Alpha plus 1, 4, 7, and yields O 7, 8 plus X. I know that looks really bad, but yeah, there we go. Alpha plus 7 plus nitrogen 14. Okay, the initial kinetic energy of the alpha particle is 7.68 mega electron volts. Determine, okay, I'm gonna, oh, by the way, these are all given, so I'm gonna highlight them blue. Determine the sum of the kinetic energy of the oxygen nucleus and X. Okay, so we have to determine the kinetic energy of these two particles after the reaction goes through. All right. So in this reaction, an alpha particle strikes a nitrogen nucleus, and then I end up with oxygen plus a proton, and this oxygen plus the proton now have kinetic energy because they were struck by the alpha particle. Okay, so solving this, I'm going to use the mass defect. So evaluate, use mass defect. Okay, so what I end up doing is I add up the masses over here, and I add up the masses over here. Okay, so the mass on the left-hand side, alpha particle plus N, have 3.7428 giga electron volts, GeV to the negative 2, plus 13.090942 giga electron volts to the negative 2, or times c to the negative 2. C to the negative 2. Okay. When I add that up, I end up with 16.837. Okay. On the other side of the equation, I have my oxygen plus my X, and I end up with 16.8383. Yields a mass of 16.83. Here. Yields a mass of 16.8383. Okay. So now I take my products and subtract them from my reactants. If I take 16.8383 and I subtract it from 16.83 or 16.837, what I end up with is 0.0013 giga electron volts. So that times c to the negative 2. So that's the amount of energy that was required for this reaction to go through. Now, the products actually have energy because there may have been energy left over. So 0.0013 giga electron volts actually equals 1.3 mega electron volts. Okay. If I take 7.68, which is the amount of energy that the alpha particle had, mega electron volts, and I subtract 1.3 electron volts, mega electron volts, times c squared, I end up with 6.38 mega electron volts. And we'll round that to 6.4. We can just write this as mega electron volts because this is energy required for the reaction to go through. All right, and that is the end of that question. Okay. Next one. The reaction in C produces oxygen 17. The other isotope of oxygen includes oxygen 19. So state what is meant by the term isotope. Okay. And the radioactive half-life is 30 seconds. An isotope is has the same proton number but a different number of neutrons. All right. For part 2 here, we're going to define the term radioactive half-life. All right, and it's the amount of time required for half of the activity of the sample, the radioactive activity in becquerels, to reduce by 1/2. Okay. Or the time for the number of radioactive nuclei to have by the original value. So it could have to do with mass as well. All right, so it's just remember the example about the tree losing the leaves. So the more leaves it has, the more the faster you'll see them come off the tree. Okay. Next question. Okay, now in this one I have to. I was given the half-life of this nucleus here. Okay. Got 30 seconds. Okay. And it contains a large number of nuclei of O19. On the grid below, draw a graph to show the variation of time with the number of nuclei of O19 remaining. Okay, and it's kind of hard to see on these graphs, but what I'm going to do is I'm going to label on here every 5. Let's do every 5. I'll label my axes. They look a little bit darker here at the 5. Okay, put in labels on these axes. Okay, and I'm starting up here. Okay, this is the mass or the activity. This is the time. Okay, or sorry, this n is the number of nuclei, but it could be activity. Okay, and I'm gonna just put my graduations here. So after 1 half-life, let's see here, I should be right here. Yeah. After my 2nd half-life, I will be right here. 3rd half-life, I'll be here. 4th half-life, I will be right here. Okay. So I'm going to try and draw this here. So actually, right here, this is 30 seconds. This is 60. This is 90. And this is 120, and that's time in seconds. Okay, and yeah, you'll probably laugh at this, trying to draw this curve. Okay, so I want to end right there. Okay, here we go. No turning back now. You'll probably do a better job on paper. Okay, that's not perfect, but it's kind of a curve. Okay, now I'm going to go down to the next one here. And I want to be right there. And actually I'm going to go, oh, not there. I want to be here. Okay, and then on the next one, I want to be right there. And then the last one, I'm right here. Okay, so now you just connect the dots here. There. There. And there. There. That's actually not too bad of a curve. All right, that's all they're looking for. You want to just make sure that the curve fits the dots. All right, and that's it. Okay.